All right, so remember, enzymes are made of proteins and they can fold into shapes and control reactions by using those shapes. And they do this by lowering the activation energy. That's the energy you have to add to get the reaction started. And this, in turn, speeds up reactions. So remember, always think of a wrench because a wrench uses its shape to make work easier and therefore speed up what you can do. So here we have a graph with activation energy. So remember, the little bumps represent the amount of energy you have to add to get the reaction started. So without an enzyme, there is a lot of energy that you have to add. That's a very high activation energy. This reaction is not going to happen very fast. With an enzyme, you dramatically reduce that activation energy. So since you don't have to add as much, it's much easier for the reaction to occur. Now, when we look at an enzyme, remember what we do is we take substrate. So that's what goes into the reaction. That substrate will bind at the active site because of the very specific shape, add a little bit of energy, and then it will create products. Now, in this case, it broke the substrate down into the products, but at the same time, it could take substrates and actually put them together to create a single product. So enzymes take substrates and either put them together or break them apart to create products. Now, the characteristics, remember that they are very specific to a substrate. It's all about the shape. So just like a wrench only works with a bolt that it fits. So enzymes only work with a specific substrate that fits in that active site. They're not used up, so they can be used over and over again, just like a wrench. And they need specific conditions. So pH and temperature can dramatically impact a enzyme. Now, remember also the amount of substrate can also impact the rate of that reaction because if you don't have substrate, you can't do the reaction. But pH and temperature can actually denature the enzymes, which means that they are destroyed and they are destroyed forever. So lastly, if we look at these graphs, let's look at enzyme B in terms of temperature and how it's going to react under different temperatures. If I want to find the optimal environment, the optimal temperature for enzyme B, I look over here at the enzyme reaction rate and I find where it is the highest. So that would be at this peak. I draw a line straight down and at a temperature of about 35 degrees Celsius, this enzyme is working at its very best. Anything different than that, and it is not going to be working as well. If I go all the way to about 55 degrees Celsius, the reaction rate has gone to zero because the temperature, the heat, has actually caused that enzyme to denature. Now, pH, let's look at enzyme A. It's working best right there, and so that's at about a pH of 6. But if that pH drops to about 2.5 or a little over 9, in both of those cases, that enzyme, that pH has been too extreme, and the enzyme has now denatured. It's destroyed. It will never work again.